तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last few lectures, we saw some elements of C programming. So I'll just summarize in this program here shown what are the things which we learned. So this program, this sample program contains almost everything which we did in the last few lectures. For example, this tells, okay, what's the header, how do one construct a program? So there is a main program. The program has a part of main body, and then there are some functions, which is the part of the program. So here, before the main program starts, you have the normal include files, which has all the libraries, math library, input output libraries, etc. Okay, and then you have some constant definitions. Here, for example, you have defined some number here. And then you have some external functions defined. For example, here I have defined an external function called cube, which is also defined outside the main program. So all external functions are to be defined outside the main program. Okay. So this, and then there is a main program, and then which calls functions. And inside the main program, we have definitions of variables, and in which we saw there are the two types of variables we can define, which is actually we can have three types. I am showing two types here, which is floating point variables and integer variables. And among the variables itself, you could have array of variables, and then we saw that we could have pointers. These are things which we saw in the last few lectures. And then we said that the pointers could be to a variable, and we said array name itself is a pointer to its the array, and we said that we could have a pointer to a function, and that's here. This is a way to define a pointer to a function. And when we said that when you define a pointer to a function, we have to say what type of argument is going to return. That's this particular function doesn't return anything, so it's void. But if it's returning an integer, then you have to say integer, and if it's returning a floating point, you have to say float. So here is a declaration of a function. Okay. So it's saying that there is a function declared here. Again, it doesn't return anything. Okay, and here is a declaration to a function pointer. Okay. Okay. So then we saw that we can have this pointers as to we can have dynamic allocation of memory, and here is a way we allocate memory to a pointer variable. So here to a pointer, and here we are allocating memory using this function called malloc. Okay. And the assignment statements, and we can, once you have allocated memory to a pointer, we can assign variables to it, and these are all assignment statements. And we said that we can, once having defined a function pointer, we could actually point that function pointer to a particular function, and that is what this statement is. Remember, I have defined this function here, and there is a function pointer, and then I can point this function pointer to a particular function. And then we saw printf statements and various formats. We saw %f for floating point printing, and %d for integer printing. And we also saw in the previous lecture that %u can be used how to print addresses to which pointers are pointing. And then this is a way to call, once you have pointed the function pointer to a function, we said we can actually call that function by invoking the pointer itself, not by these kind of statements. So that's what we have said. And now we also saw that we have declared a function as an external object, that is an external function, and having defined that way, and you could actually pass the address of that function which is declared externally to another function, and this is actually demonstrating that. Okay, we have this function called cube here, okay, which we declared as an external function, right, and we can pass the address of that function, that is by saying ampersand cube, to another function. In this case, we are passing it to my function through this pointer, function pointer. That's what we're doing. Okay, and then the function pointer, my function here, gets it as some other name. It doesn't matter, right? And then it can execute that. Okay, so again, the structure of a function here, again the type, which is void because it is not returning anything, and the name of the function, the arguments, and the argument declarations. Right? So this, as we saw, that these declarations can also be here. We could say float x instead of x, then we don't have to declare it here. Integer y of 2 we could say, or we could declare it here. Okay, so d is pointer here, okay, and power 3, what's called power 3 here, is a function. Okay, it's a pointer to a function, so that's what's been declared here. Okay, so once that's the structure of the function, and the function can then execute this power 3 by invoking that pointer. Okay, so these are the things which we saw. So we saw in general a general structure of a C program, and we saw pointers, we saw variable, both integer and floating point, and we saw character arrays, and we saw how to call a function and how to invoke a function through a pointer, and how to pass the pointer to a function through another pointer to a function to another function. We also saw two-dimensional arrays and how to point one-dimensional pointer arrays to two-dimensional arrays and read out the addresses, etc. So now in this lecture we will try to go a little more onto the way the variables are stored on a computer. Okay? We would need this before we actually understand what kind of errors a program can have and how does this errors propagate, etc. So we look at that now. Okay? So here is a picture of a vehicle's odometer. Okay? You might have seen this, everybody. And now what is the speed of, now this is, let's say this is a speedometer. So the question is, what is the speed at which this vehicle is, somebody asks you, what is the speed at which this vehicle is traveling? Okay. So then what would you say? So you would say that this is going between 48 and 49. So we can see that it's between 48 and 49 kilometers per hour. So we can say that with confidence that this is going between 48 and 49. And so then we ask for a little more. We ask for, okay, we know how much between 48 and 49. We say, okay, between 48.7 and 48.8, but that's a guess, right? So we make a 1 decimal point guess here, okay, because that's not marked on this odometer. So that's what we say. We can, with confidence only, we can say, we can make 48 with full confidence, okay. And but we can make a guess on the last digit, the 1 decimal point. Okay. So that brings in the point of what are the number of significant digits on this particular instrument. Okay. So similarly, we could also ask the question that what is the number of kilometers traveled by this particular vehicle. Okay. Then you would say that it's 87324. So that's 87,324 kilometers, and something between 4 and 5. Okay, so it's okay. I can say that 87,324 kilometers it is covered, okay, and it's about 0.4 between 0.4 and 0.5. Okay. So that's again, so we could say that okay, it's slightly less than 0.5, say 87,324.5 okay, miles or kilometers. So in this case, now we have 1, 2, 3, 4, 5. In 6 digit also we could say, okay, but the 7th digit is uncertain, completely uncertain. We don't know what it is. So now that brings into the concept of significant digits. That is, that's the number of digits we can say we can read off with confidence. Okay, so they always correspond to one digit and one estimated digit. That's what we said here. Okay, so then this is kind of an estimate, right? So we said we saw that it is between 4 and 5, and we said closer to 5, so we're just making an estimate here. So that's the number of digits which we have, significant digits. So now that's an important, so one other important concept which we would get from this is that something called a significant digit. Okay. So when you do computing also, we need to know what are the number of significant digits. Okay. So we will see that in later in this lecture, that the number of significant digits depend on what kind of arithmetic operations we are executing with what kind of numbers. Okay, so now can we just is it easy to determine the number of significant digits? Okay. It's not always so easy. Okay, so for example here let's look at that. Okay, now if you given this numbers 0.00001845, okay, or 0.0001845 and 0.001845. Okay. So now what are the number of significant digits in this? So so they all have 4 significant figures. Okay, that's significant digits. That's what the answer is. The zeros are basically used to locate the decimal point. So it's not so trivial. That's why I said. So we have a better notation when we use programs. We have a better notation to actually fix this. Okay, so that's what I'll show in the next one. Okay, so here again, for example, you could have 463000, and you could ask what are the number of significant digits in this. Is it 2, 3, or is it 5? Okay. So again, in the case of large numbers, it's not clear how many zeros are significant. We can add any number of zeros, and the question is how many zeros are actually significant. Okay, so that's not always quite clear. So the way to overcome this is to use a more scientific notation. That is, we say that we will write 46,300 as 4.63 into 10 to the power of 4. So now we say, okay, that I have 3 significant digits in this problem. Okay, so if I write 4.630 into 10 to the power of 4, then I would say that I have 1, 2, 3, 4 significant digits. That's a way of telling the reader that we have 4 significant digits. Okay. And I could say 4.6300 into 10 to the power of 4, then that will have 1, 2, 3, 4, 5 significant digits. Okay. Look at that, all of them represent the same number. Okay. It all is 46300. Okay. Now saying that whether the zeros are significant or not, okay, is represented in this format. Okay. So then there are other problems in representation of numbers. So one is this number of significant digits, okay. And then other thing is there are certain numbers like irrational numbers, right, which cannot be represented as a ratio of 2 integers. So in that case, you have, for example, here I have taken pi as an example. We know pi is 3.14159, and you can go on with this. Okay, and so this series never ends. So now the question is, how do I represent such a number on the computer? If it's a rational number, I could actually store it as a ratio of 2 integers, let's say, in a program. But if an irrational number like this, how do I store it? So I can't, right? So I have to make an approximation to this. So that brings in errors again. Okay. So, and how many digits I can store depends on how many significant digits I would have on my storage. So what is the message here is that the computers, since it can retain only a finite number of significant figures, okay, such numbers as this, that is irrational numbers, cannot be represented exactly. So there will always be some error. Okay. So those errors are called round-off errors. Okay. So we'll have to round it off somewhere. Okay. We have to say, so there is nothing called an irrational number on the computer. It's always a rational number, right? Because we're always going to chop off somewhere. Okay. So we'll round it off. That chopping or this making this infinite series into a finite series involves or puts in some error. Okay, and that's called round-off error. Okay, that's something else which we see. So we saw two things now, so that we have a concept called number of significant digits, and as a consequence of number of significant digits, we have what's called a round-off error. Okay. Okay, so then we now go into some examples of this to illustrate how do we determine the number of significant digits in computing. So let's say you represented some numbers and you're doing some arithmetic, okay, with these numbers, okay, and then the question is, as we go on, does the number of how do we retain the number of significant digits, and how do we compute what the number of significant digits are? Because a round-off error which is creeping in some point might propagate down in your program, in your calculation. So that's what we want to look at, and we have to be careful about. So now let's look at this case where we have 2.5 multiplied by 3.42. So now the question is, what are the number of significant digits? Okay. So now, the answer to 2.5 or 3.42 would be 8.6. Okay. So when we actually multiply it, and this can be, we say that it's 8.6, okay. But the question is, why are we retaining only one digit? I would say the answer is 8.6, okay. But why are you retaining only one significant digit? Why don't you retain 8.6 something, or actually, if you do this, 8.55? Okay, the answer is 2.5 given here. Okay, it's not 2.50. If it is represented as 2.50, I would have said that it has 3 significant digits. Okay. Instead of that, I have only 2.5. Okay. I have written it only 2.5. So that means it has only 2 significant digits. Okay. Now I am multiplying that by something which has 3 significant digits. Okay. So the answer will have only 2 significant digits. The third digit is not meaningful. Okay. So hence the answer to this is only, there is no point in retaining another digit. Okay, we could as well round it off to 2 digits. That's what we are doing here. Okay. So that means 2 significant figures is less precise than 3. So the answer has 2 significant figures, right? So we have 2 significant here and 3. So this is less precise than that. Okay, so we say that only 2 significant figures has to be kept. So I made use some word here called precise. Okay, so now we will see what we mean by this in a later slide. Okay. We'll look at some more examples of this before that. So here is another one. Okay, so we have 2.33 multiplied by 6.085 into 2.1. So now, I guess now it must be obvious to you that how many significant figures are here, right? Okay, we have 3 significant figures here, and we have 1, 2, 3, 4 here, but there are only 2 here. Okay, so the answer to this is obviously 2. Okay, so the answer to this, how many significant figures this particular product will have, answer is 2. So now, which number decides that? The number with the least significant figure, that's 2.1. So why is that so? Because that has the least number of significant figures. So So this slide makes it very clear that if I give a computation like this and you ask a question that how many significant figures, if you say 2, which number decides it? 2.1. Why is it so? Because that is the least number of significant figures, and that's the least precise measurement. If I had written it as 2.10 here, I would say that it has 3 significant figures. The answer to this whole question would be that this computation will give me a number which has 3 significant figures. So I hope that's clear now. So here are some practice problems and which you could write down and then work on. Okay. So just identify the number of significant figures. Okay. So here is given 3.0800 and I have given 0.00418 and then 91600, 0.003005, 3.200 into 109 and 250, 780 and followed by 6 zeros, okay, and I have 0.0101, 0.00800. So that's numbers. So you could think about how many significant figures each of these numbers have. It's trivial. You could. And then I have some arithmetic operations here. So you have 1, 2, 3, 4, 5, 6, 7 digit number added to a 2 significant digit number, okay, and then that's added to a 1, 2, 3, 4, 5, 6, 7 digit number again, and then 1, 2, 3, 4, 5 digit number. So you have some arithmetic operation, some addition, subtraction, etc. Okay, so you could work out how many significant figures each of them have, just to give you a practice. Okay, so now we go into what I said in the previous slide, that something called precision and accuracy. Okay. So let's see, we often confuse between these two words. Okay. When you say accurate and precise, what does it mean? What is meant by accuracy? What is meant by precision? Is there a difference? It turns out there's actually a difference. That is, accuracy refers to how closely a computed or measured value agrees with the real value, right? So if you say something is accurate, we know what the real value is, okay, and we say that the measured value is very close to the accurate value. So we have an idea about the accurate value, the correct value, and the measured value is how close to that is. That's what is referred by accuracy. Now, what do we mean by precision? Okay, so precision tells that how close these measured values are. Okay, so you make many measurements of some object, something. Okay, let's say you measure the length of this line. Okay, with a measuring scale, we measure the length of this line, okay, and we make many measurements and get a set of values, and how close these values are. Okay, if all the values are same, we say they're very precise measurement. Okay, but the measuring instrument you used may be not very good, and you might be getting a wrong value. It may not be accurate, okay, but it's very precise. Okay. So precision just refers to the fact that how closely each of the measured values agree to each other. Okay, so that's all the precision means. Okay, while accuracy actually refers to how close is a measured or computed value to the real value. So that's the difference, and here I have a slide which kind of demonstrate this. Okay, so one second before that, again, the precision signifies the number of significant figures. Okay, so that's the precision number of significant figures representing the quantity, right? So that's also important. How close to the real value you are. Okay, so how many significant figures you have. Okay, that's referred by precision. Okay, so that is, when you talk about that's important in precision, as I said. So here said how closely individual computed measurements agree with each other, right? So that for that the the number of significant digits are very, very important, the spread in the computation or measurement of a particular value. Okay. So that is determined by the significant figure. Okay. So here is a graphical representation of the same. Okay. Here is something, a dart board or a shooting board thing. Okay. Now this, look at this. So here one person has hit it all over here, and the accurate point should be the center of this. The correct point should be the center of this. We know that the correct point should be the center. Okay, and this person has hit it all over the place. Okay. Now you say this is, and also it's completely spread out. So you would say this is imprecise. Okay, this person doesn't know how to hit it. Okay, so it's imprecise and inaccurate. Okay, because it's huge spread. Okay, and it's completely off the target. Okay. And on the other hand, here you have pretty accurate. Okay, it's all over, it's all inside this mostly, okay, but very imprecise. Again, the spread is as large as this. There is a huge spread. So it's inaccurate, okay, sorry, accurate but imprecise. You could also look at this case, the fourth case, the third case, in which it is completely off the target, okay, but very precise. No, the spread is very, very minimal. So you probably used faulty equipment to shoot. Okay. So it has got off target, but very, very accurate, very, very precise. Or you could have accurate and precise, okay, and that is this case, okay, where everything is in the center, okay, and very, very precise. So it's at the center, on the target, and at the same time very close to each other. So that's accurate and precise. Having discussed this idea about accuracy and precision, we would see how this would come in a program because of the finite number of significant digits in a floating point number, etc. But before that, we need to understand how numbers are actually represented in a machine, right? So we said that arithmetic operations are carried out on a computer using two types of numbers, and we said they are, you have integers and floating point representations. We saw that in the program, that integer and floating point representations. Okay, so now integers we use normally for for counting numbers and for counting subscripts, superscripts, etc. Okay. So now the question is, how do we represent these numbers, floating point and integer? Okay, so first we look at the floating point numbers. Okay, so that's where we use fractional numbers. That is, when we have numbers which are not represented as an integer, then we need the decimal points, etc. Okay, so that's where we use the floating point numbers. Okay, so basically, numbers with decimal points, etc., are called floating point numbers. Okay, the real numbers are called floating point numbers. So now these numbers are on the computer. They are normally normalized. Okay, so this I will explain to you what is meant by normalized floating point representation. We will see that. Okay. So as I said here, the floating point or the real numbers, okay, are expressed as a combination of mantissa and an exponent, right? So that is, and the real number x is written as a decimal point plus some numbers, right, up to some significant digit, which is given by p here. Okay, so p here is the number of significant digits, okay, and then a base. Okay, a base what we are familiar with is 10, right? On a computer it's always 2. We know that. Right? But what we're familiar with 10. So we'll try to look at examples with base 10 to understand this representation clearly. And then there is an exponent e, right? So now beta here is a base and e is an integer. Okay, it's called the exponent. Okay, now this is an integer here. Okay, and then this is the mantissa, right? So and the p is a number of significant digits. So that's a way a real or a floating point number is represented. Okay, so let's look at some examples. Okay, here are some examples of this numbers with base 10. As I said, we would use base 10 because we are more familiar with it. Okay. So 27.39 is a real number. We know it's a real number. It's a floating point number. So how is it actually stored on the computer? It's stored. Let's say we have a base 10 computer. Okay, this is imagine. Okay. Then it will be stored in the normalized floating point representation as 0.2739 into 10 to the power of 2. So base is 10, exponent is 2, the mantissa is 2739, and the first number after the point is always non-zero. Okay, so that's what I meant by normalized. You don't put a point 0 here. Okay, you shift all the numbers such that the first number after the decimal point is non-zero. Okay, and you can adjust your exponent such that it's always true. Right? And then you have a sign. Okay, so you need to store the sign, and you need to store all these numbers. Okay, and then you need to store the exponent. The base is fixed. So when you store a floating point, and when the computer stores it, okay, it needs a bit to store the sign of the mantissa, and then it needs to store the mantissa itself, and then it needs to store the exponent and of course the sign of the exponent. Okay. So you will see that. So here the sign of both are plus. So now to illustrate this normalization, I again show this number here. So it's minus 0.00124. Right? So now that's stored in the normalized representation as minus 0.1240. Okay, so this is again showing that, okay, if I had to represent this on a to 4 significant digits, okay, then I will normalize it. I will shift this whole thing here, okay, and make it 10 to the power and put an exponent 10 to the power of minus 2, right? So minus 2 is my exponent, okay, in base 10. Right? So if I had actually 5 significant digits in the mantissa, then I have to add one more 0 here to keep that same. So the fractions found here are normalized, okay, and the first fraction digit is always non-zero. So now you think about this. What does it mean if it's on a binary machine? Okay, that is if its base is 2, okay, that would mean that this number after the decimal point is always 1, right? Okay, so that's what it means. It can be only 0 or 1, right? So and because it's a binary, and so this would mean that in the normalized representation, this would mean that this bit here is always 1, okay, because it's normalized. It can't be 0, it has to be 1, right? So it's always 1. So in that case, we don't need to store it because we know it's been told to the compiler or to the program that it's a normalized floating point representation. So that means the first digit after the decimal point, after the first digit of the mantissa is always 1 in a binary. So we don't need to store it. So that bit can be used for something else. Okay, that's what the interesting aspect is. Okay. So that is always possible. Okay, and so because this first bit of the mantissa is always 1, we don't store it. So in some of the computers, most of the machines, this bit is suppressed. Okay, as I said, we can use that for something else, that memory space. Okay, so the number of bits for a floating point is always fixed, as I said, and so that also implies, as we seen earlier, that there is a finite number of distinct values. Okay, so now we look at this by an example. So here is a case where the base is 2 and there are 2 significant digits, and you have an exponent which can go from minus 2 to plus 3, let's say. Right. So what does it mean? What are the numbers? Suppose I have a system which is like this, which is base 2, two significant digits and an exponent which goes from -2 to +3. So what are the numbers which I can store in a floating point representation, in a normalized floating point representation? That's what you're going to look at. Okay. So what can be the numbers be? The numbers can be plus or minus 0.10 base 2. This is a representation, base 2 to the power exponent e, right? Only two significant digits, and this is always 1. Right? So it can be only 1 0 or 1 1. Okay, and the exponent can go between -2 and +3. Okay. So what does it transfer to? So if it is 1 0, what does it mean? With 1 0, it is 1 by 2, right? This is 2 to the power of -1. Okay. So that is 1 by 2. Now if it is 1 1 and 2, then it is 2 to the power of -1, 2 to the power of -2. So that is 1 by 2 plus 1 by 4. Okay, so you have 3 by 4. Right. So that's the way it is represented. So now that means these numbers now can range from -6, right? So that's, let's say 1 0 is one possibility. Okay, so what is the smallest number which it could have, if you can think about, is the range of, we just saw the range of exponent is -2 to +3. So the smallest number you would be able to represent would be 1 by 2 into 10 to the power of -2. And the maximum number it could go, the smallest positive number, that's I mean, okay, the maximum number it could go would be 3 by 4 into 10 to the power of 3. Okay, that's 6, right? And so it can, the smallest positive number would be 1 by 2 into 2 to the power of -2, and the maximum would be 3 by 4 into 2 to the power of 3, that is 6. So total number it can go the full range from minus to positive, negative to positive would be -6 to +6. But note that this also, it doesn't mean that I can go from -6 to +6 in all values, right? Because there is only a finite number of significant digits here. So that would mean that I have not only a limit on the values which I can store, okay, I also have a limit on the number of values I can store in that range. Okay, I not only have the limit on the range, but I also have a limit on the number of values I can store. Okay, so there is a finite number of values in a given range which I can store. Okay. So this limits the accuracy of computation often. Okay. Even though present day computers store a large, the matrix size is very large, so this would be pretty close, but still it is not continuum. Okay. It is still a discrete set of points. That's something which you should remember. Okay, so now this diagram basically is showing that, illustrating this aspect of it. That is, it is going from. Okay, I only shown the positive numbers here. So going from some value here is close. That is 1 by 2 into 10 to the power of -2. We said so. It's 1 by 8 is the smallest which can do. Okay, and then it can go all the way to +6, but in a finite spacing. Okay. So now you can also see, we should note that the gap between numbers increases as the number increases itself. Okay, so that's also important thing to remember. Okay, so that's a important thing to remember, because that actually keeps the number of significant digits the same. Okay, so now when the number goes, if this is your representation, okay, and if you try to put in a number in this system, if you try to compute something which is more than 6, let's say you have a 2 significant digit floating point normalized system, okay, and you try to do something more than 6 into it, okay, so the maximum number it can represent is 6, as I said. Okay, so if you try to represent something more than 6, then it would give an error saying that there is an overflow. Okay, now if you try to put something less than 1 by 8, then it will say there is an underflow. Okay, so apart from this overflow and underflow errors, which we know, there are also errors there are also possibility of errors coming in because of the finite number of representation. Okay. Okay, so this is coming because there is a finite number of digits or bytes allotted for the mantissa and the exponent for any system. Okay, we will see how much that is later. Depends on the machine. Okay, so number of you need to allot certain number of bits for the mantissa and certain number of bits for the exponent, and then you have to allot one bit for the sign of the mantissa, and some cases now one bit for the sign of the exponent, but normally that's not given. We will discuss that in a later lecture, the actual implementation of this. But for the present, we understand that there is a finite number. Okay, so that's what's more important. So some examples again. Okay, so 2.26.2 is in base 10 would be 0.262 in the power of 2, right? And so we would write this, we would represent this on the computer as 0.2620 into E02. If there is 4 digits for the mantissa, then we would write it like this, and 2 digits for the exponent. Let's say we have a system in which you have 4 digits for the mantissa and 2 digits for the exponent, and this number will then be represented like this. Okay, so exponent is 0.2 and 2620 is the mantissa. So in this case, if you do some arithmetic with this number, and if this number exponent goes above 99, then it will not be able to store this, right, because it has only 2 digits. Okay, then it would give an error and it would say there is overflow. Okay. And similarly, if this exponent goes below minus 99, then again it would give an error like that. That's an underflow. Okay, so now two ways of, let's look at the way of translating, okay, a given real number into an n digit floating point number. We will represent this as FL of x. Okay, so now you're given as number and you're given a fixed number of digits, and you have said that you convert this into this fixed number of digits floating point operation, right? Like we saw pi, you're being given pi and you have said that you have a 6-digit floating point number, you convert that. How do you do this? So it's obvious that you can't represent pi accurately or completely in a finite number of digits. Right? So you have to do something to this, and that's, as I said, you either round it off or you chop it. Okay, so there is a slight distinction between rounding and chopping. Okay, that's what we would see now. Okay, so that is, for example, let's take 2 by 3. Okay, so that's a rational number. 2 by 3 is given to you, and you are asked to do it in a 6-digit floating point arithmetic with base 10. Let's say. Okay, then how do you represent that? Okay. So you have 6 digits total. Okay, so then you said that I do 4 digits for the mantissa and 2 digits for the exponent. Okay, so I have 6 digits in total. Okay, and then how do I represent it? I could write it as 6667. Okay, when rounded, because I know it is 6, 6, 6, 6, 6, 6, it keeps going like that, right? Okay, so I could say that I round it off after the 4th digit. The 5th digit was more than 5, so I round it off to the next integer here, and then I make it as 6, 6, 6, 7. That's the rounding. Or I could just chop it off, right? So you could see that they give slightly different errors, okay, depending upon whether you round it or chopped it. Okay. So as I said, to summarize this, as I said, there is this finiteness of the representation, and because there are gaps, right? So in this case it's a gap. Okay, so there's a finiteness of the representation and a finite number of floating points allowed within a given gap, and then you have overflow and underflow because of the exponent is limited. Okay, we could see this in a program here. Okay, so I have this program here which is you have a floating point n, okay, which is given as which I start with n equal to 1, okay, and then I multiply it, I run it through a loop, and then I multiply it by 2 every loop, okay, and then I am just printing out here using this percentage %e, this kind of format. Okay, I am printing out both the x value, that is 1 by of n multiplied by this 2 every time step, so it keeps increasing by 2, it just doubles every times, every loop, and I just print this out. Okay, let's see what we see, what we get. So you can see that this is the 1 by n which is doubling, so it's half, it goes to half every time step, this at every run in the loop. Okay, and this is one which is doubling every time step, every value of I. So as I increases here, this doubles and this goes half. Right? And I'm just trying to represent that using this floating point format. Okay, in this format. Okay, so we have kept it. This is the way it's printed out. It's not the way it's stored. Okay, this is the way it's printed out here. Okay, and this is in base 10. So this is printed out in base 10. And then you can see that it was going half every time step, every value of I, it was going down by half. Okay, and then it reaches 5.8 10 to the power of minus 39 here, and it reached 1.7 in 0, 1, 4, 1, 2 in 10 to the power of 38. And the next time step it says this is infinite here, and it says it's 0 here. Okay, that is, so that means it cannot represent a number which is below this value here, and a number which is above this value here. So for example, it cannot do 3.14028224 10 to the power of 38. It cannot do that. Okay, so that shows the finiteness of this the numbers which it can represent. Okay, so this m and minus m, at which it will show that here, for example, if I go by this example, that m and minus m are the lower and upper bounds of the exponent. I have taken this as same here. It may not be the same because the way it is represented on a machine. Okay, it may not be the same. So here it is minus 39 in plus 38. Okay, after that it is not able to do it. So that is the example of. That's one more example here, a 6-digit floating point. Okay, operation. So here it is 111 E51 multiplied by 444 E50. Okay, now if I multiply this, again base 10 I am representing here. Okay, I multiply this, I get something 0.04 etc. Okay, so even if I normalize this, it will get so now 0.4937284 into 10 to the power of 100. Right, so E100, okay, and then it will represent it would give that as an overflow. Okay. Similarly, this will be an underflow. Okay. So here are some problems. You could try to find the largest and smallest numbers that can be represented. If you have base 10 and 4 significant digits on the mantissa. Okay, and you have an exponent which can go from 4 to 5. Okay, so, sorry, this is minus 4 to 5, minus 4 to 5, minus 3 to 4, minus 2 to 3. Okay. And this is 16, base 16, and 4 again, 4 significant digits on the mantissa, and exponent minus 3 to 4. Base 2, 8 significant digits on the mantissa, and exponent minus 2 to 3. So if I try to find out what's the smallest and the largest number which you can actually represent on this machine. So before we actually close today's lecture, we'll just look at the integers now. We just looked at floating points so far. So let's look at integers. Okay, so now even there is a range at which for the integers too. We just saw the range for the floating points. Okay. So similarly, there is a range for the integers too. Okay. So there is, because again there is a finite number which you can store. So that here is a kind of a problem, that is, we try to determine the range of integers in the base 10 again, that can be represented on a 16-bit computer. Okay, so what's that? Okay, you have a 16-bit computer. Okay, of the 16 bits, the first bit has to hold a sign, right? The remaining 15 bits can hold binary numbers. Okay, so sorry. Okay, but from 0 to, so all zeros to you can put all ones. Okay, so you can find out if of the minimum number is everything is 0. Okay. Minimum means positive. Okay, positive number. Okay, everything is 0. Okay, that's one possibility, or everything is 1. Okay, so it's everything is 1. Okay, then you could have 1 into 2 to the power of 14 to 1 into 2 to the power of 0 summed over, right? So that's the number which you can store. That's 32,767. Okay, and then you have 1 bit for the sign, so that could be plus or minus. So you would say it could go from minus 32,767 to plus 32,767, 32,767, right? So that's what you would think. Okay, but if you ask someone that, they say that's what you can do, but but there is one, I said that there is also a 0, everything is 0, and that's kind of trivial. You don't need to store that. Everything is 0, it's a 0. Okay, so you don't need to store that. So I say that I can use that to store one more number. So I store minus 32,768 on that number. Okay, so my range now is become minus 32,768 to plus 32,767. That's the range in which I can store these numbers. We can see this in a small program here. Okay, so here I'm trying to print out the maximum value of the integer which this machine, this is a 32-bit machine, can store. Okay, so that's, I will do that here. I'll double the number, and you can see how much it can store. I've doubled the number, and I printed out both n and minus n values. Okay, so I start with n equal to minus 1, and I double it, and I print out both the positive and negative numbers. Okay, and I will also show you that I can print out. I also can do another thing. I just say start from m equal to 1. Okay, and then I run this from 1 to 30. Okay, and then I will sum up all of these numbers. Okay, so that is actually doing that sum which I showed you here, right? Okay, I'm just going to do this sum, and then you print out the number. Okay, and then you'll see what we can see in this case. Okay, so what do we see? That we can actually print out these numbers. So we see that the number keeps increasing. Okay, and the number keeps increasing, and when after it reached some number here, that is 214748368, okay, and then the next number it shows 0. Okay, it cannot represent anything more than that. Okay, then it just puts in a 0. Okay, and when I actually sum it up, I can see that this is a sum which I showed you there. Okay, and the sum, the positive value can go up to 7. Okay, and the negative value can go up to 8. Okay, so that is 214748368 is possible on the negative number. Okay, but I cannot do that for the positive number. That's what you see here also. Okay, this number, if it was this double of this, went one more than 214748367, right? It went to 48. Then it lost its sign. It became minus. Okay. It cannot represent that number. But while it has no problem with the negative number, okay, that's because of this. I use this 0, 0, 0. So that's a 16-bit number, 16-bit computer I showed here, and I showed you a 32-bit computer here. This is a 32-bit computer, can show can store from minus 2147483648 to plus 2147483647. That's what it can store. While a 16-bit computer would be able to store from minus 32768 to minus 32767. Okay, so the kind of range of integers. So we discussed range of integers and the range of floating point numbers, and it's saying that the floating point numbers are not represented as a continuum. There are gaps within the numbers, and there are errors which can appear because of this. So we stop here now, and we'll go to the concept of what's called a word out of in the floating point representation in the next.